So I will share my screen. Can you see it, I guess? Yes. And, good morning or good afternoon, everyone, depending on where you are connected from. So today I'm going to show you a bit of the research that I've done during my PhD at AMOLF. And first of all, I would like to thank the organizer of this series for the opportunity to share this work today. So during my talk, what I will discuss is essentially what is strain, so how we can induce strain in perovskite and how we can quantify this strain, but also why this strain is important for this material and for its properties. And then I will jump into the phase segregation, which is a phenomenon that is very common in mixed-halide perovskite, and then I will show you how we can stabilize this phase segregation by playing with strain. So first of all, just a summary of how you can introduce strain in a material. So there are, of course, many ways of doing that. So you can, of course, apply a compressive or tensile strain, so really squeezing the material or stretching it. But you can also apply some mechanical deformation, meaning that if you have a perovskite or another material on top of a substrate, and this substrate is flexible, you can also bend the substrate, and you can induce this mechanical deformation. On the other end, you can also play with strain by playing with the thermal expansion coefficient of substrate and perovskite. So basically what you can do is that you can change the amount of strain that you have in your material by choosing the two materials with very different thermal expansion coefficient. And this means that, for example, if you have a material that require an annealing, for example, the perovskite, and then you cool down at room temperature, so you will have a certain delta T. And then if the thermal expansion coefficient of the perovskite and the substrate is the same, then you get basically no strain. But then if one of the two is higher than the other, then you have some stress in the film, so during the film formation. Another way of having strain in the material is also by playing with lattice mismatch of materials. So that means that if you have two materials, let's say A and B, and they have the same lattice mismatch, they do not have to accommodate strain because they perfectly align one on top of the other. But then if you have material with different lattice parameter, then you have to accommodate this strain. And that means that you will have a buildup of strain in your material at the interface between them. It's important here, and I really want to mention this, that usually we do not have only one type of strain in this material, in any material, because strain can originate from many sources, and usually you have always a combination of lattice mismatch, thermal expansion mismatch, and even mechanical deformation. Going now to how to quantify strain. So we can, so there are many ways of quantifying strain, and I will present here two of them, which are the bulk modulus and the Young modulus. So basically the bulk modulus is how a material is sensitive to a compression that comes from all the direction. So for example, in this case, you have a compression of the entire volume because you apply pressure from all the direction. And here in this table, I just summarized some very compressible material and also stiff material. So for example, you have here steel and silicon, gallium arsenide. Their bulk modulus is very high, meaning that it's not easy to compress them. But then if you look at the end of this table, you have rubber, which is very low, but also the perovskite, which are very low and different compared to the silicon or gallium arsenide, meaning that we can, so they are more sensitive to strain. The Young modulus is quite similar, but then the difference is that you apply a compression or tension along one specific direction. And in this case, we have to keep in mind that when we apply pressure on one direction, we also have tensile stress on the other direction, because we have to keep the same volume. So it's not so only compression that we have in the system. And here again, you see in this table that still silicon and gallium arsenide, they have very high values. And here you have also the direction along which you apply the stress. And again, the perovskite fall really at the bottom of this table, meaning that again, perovskite are very sensitive to external stress. So this all to say that so perovskite are very sensitive to stress, and this has been found in many properties of this perovskite. So in this slide, I just picked 3 of representative works where they show the effect of strain. But there are, of course, many more that you can find in literature. And so the effect of strain on this perovskite is shown in this paper, where they look at the effect of strain on top of the film, so very far from the substrate, and then in the slope. So meaning that they probe closer to the interface between the substrate and the perovskite, and they found an increased strain in this slope, and this affects the stability of solar cells. So, for instance, you see here that strain-free perovskite has a much longer lifetime than a strained one, but also you have effect on the efficiency itself, and also on ion migration, which is something that probably you are a bit more familiar with. So in this perovskite, you have movement of ions, and depending on the type of deformation that you apply, so concave or convex, then you have lower or higher activation energy. And this summarized in this plot, where you see that the activation energy decreased as a function of increased strain. So what we wanted to then do was to look at the effect of strain on phase segregation. And this phase segregation is something that occurs in mixed-halide perovskite, which are very popular because you can tune the bandgap of this material from the UV to the infrared just by mixing halides in different ratios. But then, of course, there is a problem. This problem is phase segregation, and it's a mechanism where it's a process where you where in the perovskite you have movement of halides forming halide-rich domains. So that means that so if you have your perovskite in the dark, you have a lot of bandgap fully tunable in the visible, but then when you start to light soak, then the emission will only come from an iodide-rich domain. And of course, this is not good if you think of tandem solar cell or LEDs. The hypothesis for this was, so there are actually a few hypotheses for this phase segregation, and one of them is a phase transition from tetragonal to cubic, which occurs at 0.2, so when the composition has 20% bromide. And so basically the idea was that below this threshold, the perovskite is in the tetragonal structure and it's fully stable, but then above this threshold, you start to have a cubic structure, which is not stable anymore against light. And a second hypothesis was more related to strain in a way, and related to the Gibbs free energy of mixing. So the idea was that in the dark, this delta G was negative for all the composition, so basically no phase segregation. But then when you have light, you have a positive delta G above this 20% bromide incorporation. And in this delta G mix, there are two terms. One term is the enthalpic term, which is closely linked to strain, and in particular to lattice mismatch when mixing iodide and bromide in the same perovskite, and an entropic term. So what we wanted to do was then look at how strain could affect this phase segregation. And how we did that was to not focus on photoluminescence-based technique, because we think that in this case, photoluminescence can only give a partial picture of phase segregation. And the reason is that when you have a mixed phase and you illuminate, so you form bromide-rich domains and iodide-rich domains, all this charge will funnel into the low energy states. So we will mainly probe the iodide-rich phase. And this is something that it's only like a partial information of the phase segregation. So then what we wanted to do was to use transient absorption spectroscopy, which is based on absorption. So we don't have anymore the problem of the photoluminescence-based technique. And here you have the setup where we so that we have this pressure cell that I will show you in a bit how it's done. So we have a pump light that excites the sample, a probe which makes basically a photograph of the system at a certain delay time between pump and probe, and then we have a light soaking beam, which is the trigger for phase segregation. And the type of output that we have from this experiment is the differential in transmittance when the pump is on and when the pump is off. So of the system, when it's excited and when it's not excited. So the information out of this technique is very sometimes very complicated because you can have many signals. And the one that we are focusing on is the ground state bleach, which is the excitation of this charge to the excited state. And it's usually, so in this configuration is positive. So the reason why it's positive is that, so when you have your pump off, so you only have the probe light and that interact with your population in the ground state. So this probe will be absorbed, and that means that the transmittance after the sample will be very little. But then if you excite with a pump, you have excitation of this population with the excited state. And when the probe comes, the transmittance of this probe will be much higher. Therefore, the transmittance when the pump is on is higher than when the transmittance, when the pump is off. And this signal then is positive. So what we then did was to pick pressure, but why? So this is the pressure cell that we have used. So it's really a bulky pressure cell with 4 windows, and it's filled with liquid. This pressure cell is connected with a manual pump. And what we do with this pressure cell is really increase the amount of liquid that we have inside the cell. And this liquid will then apply the pressure to our material. So the reason why we pick the pressure and this particular system is that if we start from a composition like 50% bromide and 50% bromide iodide, which is cubic, the pressure range that we look at is a pressure range where we do not have any phase transition. So that means that in principle, if the problem is really the phase transition, then we should not see any difference with pressure, because it's still cubic, so should still segregate. But then the other reason was that actually strain can be used to tune the enthalpic term of the Gibbs free energy. So we can at least have an idea if this hypothesis is convincing. So before to jump to the result, just a picture of our pressure cell and a common diamond anvil cell. So this is probably something that you have seen more often. So the main difference between the two systems is that the pressure in our case is isotropic, meaning that the pressure applied from the liquid is the same in all the direction. And in the case of the diamond anvil cell, you have a directional compression, because you have 2 diamonds and you basically squeeze your material from the top and from the bottom. So it's really along a certain direction. In addition, you also have, in this case, you might have some shear stress that comes from the high pressure and the fact that there is some contact between the diamond and the surface of your perovskite. And another important difference is the pressure range that we can achieve. So in our case, the pressure range is between 50 megapascal, so 0.05 gigapascal to 0.35. And in the case of the diamond anvil cell, it's only above 1 gigapascal, and already 1 gigapascal is quite low for a diamond anvil cell. So now you might wonder, okay, but what's the problem? Of course, if we want to have our device that work, I mean, we cannot have device that work under pressure. So we have to implement this pressure or strain through fabrication. And that's something that we can do for low pressure range. So we can have this type of pressure during fabrication, but we cannot have gigapascal pressure during fabrication. So for example, the playing with substrate and thermal expansion coefficient can result in this type of strain, but not in this type of strain. So this is too high. So then going to the experiment. So first of all, what we did was to check whether we could monitor phase segregation. And what we did was to measure transient absorption spectroscopy at ambient pressure of this composition before light soaking. And here we see only one positive peak, which corresponds to the absorption of the mixed halide phase. And then what we did was to illuminate the sample, repeat the same experiment, and then we found two domains, so two positive bleach. One attributed to the bromide-rich phase because it's blue shifted in comparison with this, and the other one is the iodide-rich phase because it is at low energy. So at this point, of course, this is a delay time between pump and probe, and what we want to see instead is the delay time in real time. So what we did was to pick one delay time between pump and probe and then measure as a function of real time. And the reason why we picked this 15 picoseconds is because it's in our condition, this moment is this time is after the hot carrier cooling of this system, and it's also before recombination in the system. So we now fix the delay time and we do the real time experiment. So immediately we see that when you start light soaking, you have the formation of bromide-rich phase and again iodide-rich phase. So it's really something super quick, so within 1 or 2 seconds. Then we moved to another spot and we increased the pressure and we did the same experiment. And what you see here is that actually when you go to 0.3 gigapascal, the picture of your system is completely different. So you have only one peak, which corresponds to the mixed halide phase, and you have more or less suppressed all the phase segregation. It's not fully suppressed because you still see that there is some broadening of this peak, which indicates that still some phase segregation is happening. But clearly the effect of compression is evident between the two, if you compare the two. So now if we plot the peak energy as a function of real time, so the peak energy of the bromide-rich phase and the iodide-rich phase, you obtain something like this. So basically you have the evolution in time, in real time, and as a function of pressure of the two domains. And you can see already that initially you have a change in the composition of your perovskite, but then at some point it stabilizes, meaning that the composition, even if you illuminate for longer time, you don't have any change in the final composition. And this kind of plot can actually give us two types of information. One is related to the composition in bromide of the bromide-rich phase and iodide-rich phase by looking at the end of the process. And the other one is the evolution of the rate of the phase segregation. So I will start with the first one, so about the terminal X value. So here again, you see that at ambient pressure, you immediately see the formation of the low energy phase, while at high pressure, you see a broadening, and probably this is also a second peak, that it's not at the same energy position as at ambient pressure. And if you plot all of this in one graph, so if you plot the unit cell volume, so the composition as a function of the unit cell volume, so what you see is that at ambient pressure, so when the unit cell volume of your perovskite is larger, you have different bromide percentage in the bromide rich phase and the iodide rich phase. But then when you start to compress, so when you have your unit cell volume smaller, the bromide composition, so the bromide percentage in the two bromide rich and iodide rich domains becomes very close to the initial mixing ratio, which in this case is 50%. And that's the case also for the 70%. So it's not, so this finding is not limited to one composition, but we have seen also in other intermediate compositions. And this one is just as a reference, this is the 25% bromide that segregate only a little because it's just above the threshold for the phase segregation. And here you see that immediately after the first data point, so at the first pressure accessible, we don't have any more change, so meaning that it's fully stable. So from this, clearly, the phase transition is not the reason of phase segregation, because the system is still in the cubic phase, but still we have a suppression of this process. So then another thing that was, so how do we explain this? So we explain this by looking at this delta G mix, and in particular to this delta H mix, because as we said before, the delta H mix is closely linked to strain, and the bromide and iodide, they have also different bulk moduli. So that means that when you apply pressure, one of the two domains, and I'm talking about the iodide one, because it has a lower bulk modulus, will compress more than the bromide one. So what we think that is in this case is happening is that the iodide compress more and accommodate more easily the strain. So the lattice mismatch that generates the delta H mix goes down. And if this goes down, of course, this delta G mix goes also down because it becomes more negative. So we think that at ambient pressure, so the phase segregation is driven by enthalpy, the enthalpy term, which is high, very high. But then when you compress, the entropy drives the phase segregation, because then this term is more negative, and therefore the delta G is more negative. So finally, also we had a look to the kinetic trace, because as I showed you before, also the kinetics was quite different as a function of pressure. And in particular, you can see that for all of this composition that we have studied, the rate of phase segregation is much faster at small pressure, at low pressure. So, and it's and that's basically the same for all of them. And by looking at the diffusion coefficient formula, we found that the logarithm of the phase segregation rate, which is this K, is mainly proportional to the activation energy. So what we think now is happening is that we have an effect not only on the delta G, but also on the activation energy for these halides to move. Therefore, when you increase pressure and you compress your system, you are also increasing the activation energy for these halides to migrate. So in conclusion, I have in this talk I've shown how you can induce strain in your material, and that's true, of course, not only for perovskite but also for other type of material. How you can quantify this strain by using a bulk modulus and a Young modulus. And then I showed you how you can measure phase segregation with technique that do not rely on photoluminescence. And we found that strain has a huge effect on both the kinetics and thermodynamics of phase segregation. And in particular, that we can use pressure to suppress phase segregation, but also to increase the activation barrier for this halide migration. And then finally, I also want to acknowledge all the people who were involved in this work, all the people from AMOLF, especially Bruno, who was my supervisor at that time, Eline, and Professor Aaron Walsh. So he did, together with his students, some computational computations that I could not show here in view of time. And of course, I thank you for the attention, and I'm really curious to hear your question.